next talk, and it'll be given by Eric Walkenshaw, who will tell us about an error-tolerant type system for variational lambda calculus. Please.
Okay. All right. Sorry. All right. So variational software is just software that can be used to statically generate program variants. So the classic example of this is the way if-def statements are used in the C preprocessor. So here we have some C preprocessor annotated code, and it's small because you're not supposed to read it. The important thing is that it's got if-def statements in it. And so by setting the macros that are referred to in the if-def statements to different values, we can run the C preprocessor and generate lots of different program variants. And each one of these variants might have different features or might run on a different platform. And our goal is we want to make sure that every variant that can be generated from a piece of variational software is type correct. So sort of the naive approach is just to generate all of the variants and type check them individually. But the problem is obviously that this doesn't scale. So even for a relatively small number of variables, it's going to be infeasible to do this brute force strategy. So what we want to do instead is we want to type check the variational program once, and if this is type correct, then all of the variants that we generate, that we can generate, will also be type correct. So here is a simple variational functional program in a Haskell-like language. So this is 4 variants of a function for looking up values in a list of key value pairs. And we can vary this function in 2 different dimensions. So first we can vary the argument type, so we can either give it an example value to look up, or an example key, or we can give it a predicate on the keys. And we can also vary the return type, so we can either return the first value that's found, if any are found, as a maybe, or we can return a list of all of the values that are found. And so we can represent all 4 of these variants in a single variational program using this notation here. And these colored annotations here are called choices. And so you can think of a choice as just like a more structured if-def statement. So each choice has some number of alternatives and an associated dimension. And the key thing about choices is that all of the choices in the same dimension are synchronized. So if we choose the left alternative in the arg dimension, we're going to get the left alternative in all of the arg choices. So here's our 4 variants here expressed in a variational program using choices. And we can reuse this choice notation also at the type level. So here's a Haskell-ish looking type. I left out the class constraint here, or the EQ constraint. But here we have our type, our variational type that corresponds to our variational program. But the problem is there's a type error in our variational program right there. So when we choose the right alternative of the arg dimension, we need to pass a predicate here, but K has the type A. So this is a type error. So with the brute force approach, we can type each one of these variants, and we can figure out exactly what variant our type error occurs in. But with the variational approach, it just fails. So what we want to do instead is make this more robust. So that's the goal of this work, is we're extending our existing variational type system to make it error tolerant. So what we want to do is we want to infer types that contain type errors in them, so that indicate which variants the type errors appear in. So in this case, this says we have a type error in the right alternative of the arg dimension and the right alternative of the res dimension. We indicate right alternatives with these little squiggles. The left alternatives don't have squiggles. Okay, so this extension is practically motivated by basically 3 concerns. So the first thing is we want to determine which variants have type errors in them. We also want to be able to recover from errors so that we can continue the type inference process and find all of the errors in a variational program. And we also want to support incremental development. We want to be able to let programmers write some variants while leaving some variants undefined or incomplete or not type correct. Okay, so first I'm going to talk about how we extended, well, I'll give some background on variational type system and how we extended to make it error tolerant. And then I'll talk about how we solve the unification problem for variational programs that can contain type errors. Okay, so instead of working with Haskell, we work with a simpler language here, the Variational Lambda calculus. This is just like other lambda calculi, but extended with choice types, and we also have constant types here, or constant values, sorry. And so again, the choice is just a dimension and then 2 alternatives, a dimension and 2 alternatives. the types of these expressions we've got constant types and type variables and function types. And then we also have choice types. These are just the reflection of the type level of these choice expressions. And then we also add an error type. This is the new type introduced by this extension. And this just indicates a location where we have a type error. Most of the typing rules are similar to other typed lambda calculi. The choice rule is also very straightforward. We just type the two alternatives and then construct a choice type from these two alternatives using the same dimension name that appeared at the expression level. The interesting rule is the application rule. So this is the unextended application rule. This is for variational typing without this error-tolerant extension. And you can see it's almost just like the application rule for other typed lambda calculi, except that we, instead of requiring that the two argument types are equal, we instead have this equivalence relation here. So this is basically a loosening of the requirements on the argument types. And just a simple example to demonstrate why we need this. Here's the function even, which is of type int to bool, applied to a choice between 2 and 3. So we have a choice between two integer values. And int and a choice in dimension a between int and int, these are not structurally equal, but this variational program can never go wrong. No matter what alternative we select in a dimension, we're going to get a type correct program, because we're going to get even applied to an integer. So we need to loosen this. And so we have a set of equivalence rules that basically define when two types are equivalent. And equivalent basically means that when we apply the same selection to both sides, we're going to get the same types at the end. Okay, so to support our extension, what we need to ask is, when can this rule fail? Because whenever this rule fails, we need to introduce error types into our result. So there are basically two ways that it can fail. The first one is if the left-hand side, if the left-hand side of the application is not a function type. That is one way this typing rule can fail. The other way is if our two argument types don't match. So again, in both of these cases, we want to introduce error types. So here's our extended or revised typing rule, and you can see this is more complicated. And I'm going to step through each of the pieces here. So the first thing we're going to look at here is this part highlighted in purple. This is an operation that's going to attempt to lift the type of the left-hand side of the application into a function type. And if it fails, it's going to introduce error types. Or it's going to introduce error types if that transformation is not possible otherwise. So just as an example of what this function lifting operation does, here's a successful one where we don't have to introduce error types. So we've got, we apply this lifting operation to a choice between two functions, and we can basically just factor the function type out of the choice, and we get a function type where both the argument and the result type are choices. In this case, we can't factor the function type out without introducing error types, because only the left alternative of the choice type is a function type. So now we have a choice. So now we have, again, a function type where both the argument type and the result type are choices, but we have error types in the right alternatives because this lifting was unsuccessful on the right-hand side. Okay, the second case, or the second way that we can introduce error types is if our argument types don't match. So here we have this little bow tie operation. This represents an attempt to match these two types. And this is basically the error that occurred in our lookup list example. So here we have the function look, which our expected type of it is given there. We expect the first argument to be a choice in our dimension between a key of type A and a predicate of type A bool. But instead, we're given an argument of type A. So we try and match this choice type to this A type, and what the result is going to be a typing pattern. So this typing pattern is this arg top bottom here, and what this means is we have a type error in the right alternative of arg and no type errors in the left alternative of arg. So this is basically an abstraction of variational types. And what we do with this typing pattern is we use it to sort of propagate the type errors that we encountered onto the result types. So if we found a type error when we were matching argument types, we need to propagate this type error onto the result types. So we call this masking. So here we've got our typing pattern that we produced in the matching stage, and we're going to apply that to our result type of our function, and we get this new result type here where we now have a type error in the right alternative of the arc dimension. Okay, now the hardest part of variational type inference is the unification, is solving the unification problems. So just to quickly demonstrate the way we do variational unification, here's a variational unification problem. We've got, we need to unify two choice types. In this case, our choice types are in the same dimension. The main decomposition method we use here is decomposition by alternatives. So the idea here is that if we select, so we can either select the left or right alternative in the A dimension, and all of the choice types in that dimension will be synchronized. So we can solve this in two subproblems here. We can choose the left branch and solve the two left alternatives, and choose the right branch and choose the two right alternatives. But in this case, it doesn't work out. So now we have to unify A to both int and bool, so we're stuck. So it looks like at first that these two choice types can't be unified. But actually there is a unifier for these two choice types. So if we map A to this choice in dimension A between int and bool, when we substitute this into our two types above, we're going to get, well, if we select, if we select the left alternative, we'll always get int. If we select the right alternative, we'll always get bool. And that's because all of these choices are synchronized. So this inner choice is sort of dominated by the outer choice. So we have a unifier here, and we didn't find it with this sort of naive decomposition by alternatives. So what we do is, the key observation here is basically that even though these two type variables have the same name, they're actually in some sense independent. So they have the same name, but we can only ever select one of them at a time because we're either going to choose the left branch or the right branch. So what we do is we qualify these type variables by adding subscripts to them to basically distinguish them. So any type variables in the right alternative of a choice, we add this A squiggle to it. That means it's in the right alternative of an A choice. If it's in the left alternative of an A choice, we just add an A subscript to it. So now we can decompose this problem by alternatives, and we can solve the qualified problem. So we get this mapping here as a solution. And now what we're going to do is we're going to transform this solution to the qualified problem into a solution to the original problem. And the process we use to do that is called completion. And what this basically does is this takes all of the variables that have the same name but different subscripts and builds up choice types using the subscripts. So it's going to basically populate the leaves of this tree using the subscripts. Okay, so in this case, so we successfully unified these two variational types. In this case, we also need to produce a typing pattern which represents whether there were any errors, and in this case there weren't. So we have this typing pattern top, which just means there was no type errors here. So let's look at a case that does have some type errors. So now we want to unify two choice types in different dimensions. So we're going to unify a choice in dimension A with a choice in dimension B. So the first thing we're going to do is qualification, just like we did before. So we qualify our A type variable and our B type variable. Now our goal is to somehow decompose this by alternatives. That's what we want to do to try and make these problems smaller. But we can't here because these choice types are in different dimensions, so they're not going to be synchronized. So what we do in cases like this is we have two operations that basically transform the problem into one that we can decompose by alternatives. So we find a choice type, we find a type variable that doesn't have a subscript in the choice we want to decompose with, and we split it into two type variables in that choice. So this is the split operation here. So this basically just introduces a new choice type that's sort of redundant in some sense. But then what we're going to do is we're going to factor that choice type to the top level so that, using this hoist operation, so that then we can decompose by alternatives here. So now we get these two subproblems after decomposing. The right-hand side is done. We have a type variable unified with something else, so we can just create a mapping for that. The left alternative, we can decompose again. I didn't show there's sort of an implicit introduction of a choice in dimension b between int and int. If we have a constant type, we can always sort of decompose by alternatives using this, by introducing this sort of dummy choice. So we again, we have two subproblems here. The right subproblem is done, and in the left branch we have a type error. So we need to unify int and bool. Can't do that, so we have a type error. So the goal throughout this unification process is to find a unifier that is most general in the normal sense. So this is our usual goal when we're doing unification. But we also want to find a unifier and a typing pattern that produces a most defined result type. So what this means is we want to have type errors in as few variants as possible in the result type. And it's not immediately obvious that it's possible to always find unifiers that satisfy both of these constraints, but in fact it is, and we can basically use this decomposition structure to produce this unifier and this typing pattern. So the way we do this is we take all of the solutions, or we take all of the branches that succeeded, and we use these to build a qualified unifier and then complete it into a unifier. So we've built our qualified unifier here just by sort of turning these unification problems into mappings, and then we use this completion process that I described before to turn this into a unifier to the original problem. And then we take our unsuccessful branches and use those to produce the typing pattern. So in this case, we had a type error in the left branch of a decomposition in the A choice and the left branch of a decomposition in the B choice. So our resulting typing pattern is going to have a type error at the leaf corresponding to the left branch of those two choices, and it's going to be type correct everywhere else. Okay. So variational type inference is much more efficient than the brute force approach. There's basically two forms of sharing that it exploits to be more efficient. The first is that choices are localized, so choices express differences between the variant programs at a local level, so we can share the common context. We can type the context once and reuse it in both of the variants. The other way is a bit more subtle. Often we have the case where we have a choice between two expressions that have the same type. So we have a choice between two expressions that both have type T. In this case, we can basically eliminate this variation at the type level. So since types are an abstraction of expressions, we can often simplify the variational structure at the type level compared to at the expression level. Okay, so that's why variational type inference is more efficient. The extension that I described here, again, is practically motivated by these three concerns. We want to know which variants have type errors. We want to be able to find all of the type errors in a program, and we want to be able to allow developers to work on some type variants without having completed the other variants. And the overhead of this extension we determined experimentally to be about 30%. The way we did this was we randomly generated expressions that were, well, pseudo-randomly, I guess, because we generated them to sort of incur our worst case expected performance for this extension, but still be type correct, so we can compare it to the unextended form, and it added about 30% overhead to include the extension in the type system. So, thank you.